Hello everyone, this is Evgenii Kovrigin, Notre Dame NMR director. I will begin with reminding us about how NMR signal changes with the molecular size. Molecules come in different sizes, and that significantly impacts appearance of NMR signals. Smaller molecules produce sharp, narrow peaks. Larger molecules generate progressively broader signals as the molecular weight increases. It is not only the molecule's weight, but its aggregation state that determines NMR line width. Molecules forming clumps or aggregates exhibit broader signals than if they are monomeric. Aggregation is often a result of unfavorable solution conditions. When the solvent is not very compatible with your compound, your molecules cluster to minimize solvent contact. This can lead to visible precipitation, phase separation, or formation of suspended aggregates in seemingly clear solution. By choosing a different solvent or making a solvent mix that better interacts with your molecule, aggregation can be reduced, yielding sharper NMR signals. NMR spectra can reveal aggregation and help us find better solution conditions. You can compare NMR spectra from your molecule in solvents of different polarity and hydrogen bonding ability. Changes in a peak width of NMR signals may indicate whether your molecule is aggregating, helping optimize solvent for better solubility and to yield narrow and better resolved spectra. Aggregation or oligomerization is often scientifically meaningful. Some molecules naturally form oligomers, and their aggregation state changes due to chemical reactions or ligand binding. These changes in the aggregation state can be monitored by NMR, providing insights into molecular mechanisms. It's easy to observe the line width of the NMR signal. Unfortunately, interpreting its meaning isn't simple. Line width alone is not enough to tell whether the molecule exists as a monomer, dimer, or part of a larger aggregate. Chemical exchange processes between molecules or conformational transitions can increase line width even if molecular size remains the same. To more directly access the size of molecules in solution, we will measure their rate of movement or translational diffusion. Smaller molecules diffuse more rapidly than larger molecules or aggregates. We can detect this translational movement and calculate the diffusion coefficient. This quantity will contain information about the size of the moving particle. To measure a diffusion coefficient, we need to create a situation where the NMR signal senses the molecule's diffusion speed. As you remember, the NMR magnet makes a strong magnetic field within the sample, and shim coils ensure this field is identical throughout the sample. Now, let's add a new magnetic field that increases along the length of the tube. The molecules will experience different magnetic field strengths as they move. A specialized NMR pulse program can detect these differences for every molecule in the sample. The core concept of diffusion NMR is straightforward. We allow molecules to move freely for a specific duration of time and then observe the variation in the magnetic field they encounter. The faster a molecule moves, the greater the difference will be between the magnetic field where it started and where it arrived at. While molecular movement is random, we focus on the distance traveled along the tube to gauge translational diffusion speed. There is a whole family of pulse programs designed to measure translational diffusion with best accuracy and sensitivity. They all operate by the same principle, therefore I will focus on the original experiment to demonstrate what they do. We begin with the RF pulse on the nucleus we want to observe: proton, phosphorus, or anything else. The pulse magnetizes all molecules in the NMR tube. Next, we do a gradient pulse along the tube length. We wait some amount of time and apply the second gradient pulse with exactly opposite magnetic field strength. If the molecule did not move during the waiting period, the second gradient pulse exactly cancels the effect of the first pulse and there is no change in signal intensity from such a molecule. Any molecule that traveled along the tube will experience different magnetic field during the second gradient pulse. The gradient effect on this molecule will not cancel exactly, and some signal will be lost. Fast-moving molecules may diffuse to a location with magnetic field strength so different that the signal will not be detectable at all. There are several parameters that have to be carefully optimized for the diffusion experiment to work. First, it is a recycle delay of the pulse program. Diffusion measurement requires full relaxation of nuclear spins to equilibrium between transients. In a Bruker system, pre-scan delay D1 and acquisition time AQ added together should be equal or greater than 3 times T1 longitudinal relaxation time. Next, we make sure that the 90-degree pulse is accurately calibrated. In the Bruker system, we can use a pulsecal command. Next parameter we have to deal with is the diffusion time, labeled D20 in the Bruker system. This time interval is chosen as a compromise between needs of smaller and larger molecules in your sample. If it is too small, the large molecules will not have a chance to move enough, and you will not be able to determine the diffusion coefficient. If D20 is too large, small molecules will diffuse too far for the signals to be detectable. In addition, nuclear spins relax during D20 and lose magnetization. Therefore, the larger D20 is, the less sensitive your diffusion experiment becomes. Our final parameter to optimize is the gradient length, labeled P30 in the Bruker system and a lowercase delta in the literature. The longer the gradient, the stronger the effect on the NMR signal. If P30 is small, slow-moving larger molecules may not experience enough of the magnetic field change along their short diffusion path. Increased P30 will reveal diffusion of larger molecules, but will make smaller molecules experience too much of the magnetic field change, so they will lose signal in the same experiment. The overall effect of the gradient length on the diffusion experiment is much stronger than the effect of diffusion time. On our systems, the P30 ranges from 0 to 3 milliseconds, while D20 has to be much larger, from 20 milliseconds to beyond 100 milliseconds. As a result, relaxation losses do not increase as much when P30 is increased. A rule of thumb: when optimizing diffusion parameters for a larger molecule, start with increasing the gradient length. If you reach the maximum allowed value of 3 milliseconds for P30, begin increasing the diffusion time. Finally, I will outline a general workflow for optimization of the diffusion series. We will choose the gradient length and the diffusion time, and collect a series of spectra with increasing signal attenuation due to diffusion. We want to measure peak intensities and plot them to fit to the exponential equation to obtain the diffusion coefficient. To create such a spectral series, we will keep P30 and D20 fixed and gradually increase the gradient power from 2% to 95% of full power. To make sure that we have picked optimal values of P30 and the D20, we will record spectra for the endpoints. Minimum and maximum gradient powers, 2% and 95%. The best quality data will be expected if the ratio of peak intensities is 10 to 1 or 20 to 1. If the ratio is too close, not good. We are not sensitive enough to diffusion. Increase P30 and then D20. If the ratio is too high, reduce D20 and then P30. Important: you must have enough scans to have signal to noise in a 95% spectrum of at least 5 to 10.